Okay, this one is Giancoli Physics AP Physics Edition, 7th edition. We are in Chapter 10, Fluids. We're on problem number 55. Let's go ahead and jump into it. Problem 55 reads, in figure 1054, which is the figure below, take into account the speed of the top surface of the tank and show that the speed of fluid leaving an opening near the bottom is given by that equation, where the height is the difference between y2 and y1, and a1 and a2 that are the areas of the opening and of the top surface respectively. Assume area 1 is much less than area 2 so that the flow remains nearly steady and laminar. That's a topic that we'll discuss separately, the laminar flow. But go ahead and wrap your brain around this problem and come back when you're ready to talk about it. Okay, this problem is slated as a level 3, probably just because there's no numbers in it, but honestly this is not that difficult of a problem because we're talking velocities and areas here, fluid flow, and the section of the book it's in. You might assume this is a Bernoulli's equation type problem, and it is. Now, the only thing that's a little bit different here is oftentimes we have similar problems to this. We'll oftentimes assume this velocity here is 0 because we assume this area is so much larger than this area here that this is relatively motionless, that we're assuming this velocity is much higher than this one. We essentially ignore this one. If you notice the result here, if the area of 2 is much larger, then this term here goes to 0, which makes this 1, and you end up with the velocity is just root 2gh, which is what you would get if you were doing this problem and assumed that your velocity up here was 0. You just end up with the hydrostatic equation from the hydrostatic pressure up here to a velocity down here. So that may look familiar to you. We usually ignore this, but we're going to go ahead and prove this equation here. So again, as expected, we think this is probably a Bernoulli's equation type problem. We're going to do that. Now we're dealing with areas here and velocities. And since we don't have velocity 2 over here, strong suspicion we're also going to use our continuity equation to translate from velocity 1 to velocity 2. So let's go ahead and grab those equations. We'll start with Bernoulli's here. Now when we apply Bernoulli's equation to our problem, we do have a height difference, so we're going to keep the y's in there. We do have a velocity difference, so we're going to keep those in there as well. Now technically, is there a pressure difference between 1 and 2? Yes. From this height to this height, there is a difference in the atmospheric pressure. So those pressures will be slightly different. But as per usual, with this being water that's 800 times denser than air, the difference in that pressure is going to be very minimal relative to the water pressure. So to simplify our problem, we're going to go ahead and ignore the pressure difference there because it will be very small relative to the rest of our values. And notice once the pressures are gone, every remaining term has the density. We can divide the density out, and those go to 0. I'm going to go ahead and simplify this equation for now without rearranging it. That's gy1 plus 1/2 v1 squared equal to gy2 plus 1/2 v2 squared. Now the reason I didn't do a whole lot more algebra beyond that just yet is I know our final answer here doesn't have velocity 2 in it. So we're going to use the continuity equation over here to substitute that out. Once I do that, I'm going to have multiple terms here of velocity 1, and that will affect our algebra. So that's why I held off. So if we use our continuity equation here to replace velocity 2, that's going to be velocity 1 times the ratio of the areas of area 1 to area 2. So if I make that substitution, remembering to square everything, I'm going to go ahead and multiply everything by 2 as well to get rid of that half because those are annoying. We get 2gy1 for multiplying by 2. We get v1 squared, which is the one thing I'm looking for in my final expression here. Again, multiplying by 2, so that's gy2. Multiplying by 2 gets rid of this half, and I end up with v2 squared here, but I'm substituting in this relationship. So that's v1 squared times a1 a2, both of those terms squared. I got two terms of v1 here. I'm going to move this term to the left while moving this term to the right. I'll go and factor out as well. So it's v1 squared times the quantity 1 minus a1 squared over a2 squared. On the right-hand side, I'm going to get 2g times the quantity y2 minus y1 after I factor out the 2g. Now I can replace this y2 minus y1 with the height, because that's my final equation has in it, what I'm looking for. So I can replace that with h. At the same time, I'm going to divide by all of this to get v2 by itself, or v1 by itself, then take the square root. So replacing y2 minus y1 with h, dividing by the expression next to v2 squared over there. Then taking the square root to get a single v1 on the left. We end up with this expression, which is exactly what we were asked to come up with. So again, slated as a level 3 problem, but really not bad. That'll take care of this one. See you on the next one.